Today's session this session will be led by Mr. Manoj Bhataria, who is the CTO at Devlata Technologies. We're very thankful to him who he has very graciously agreed to, take the session today. So Mr. Bhataria completed his BTech and MTech from IIT Bombay, and he is a very seasoned analytical scientist with over 25 years of experience in particle characterization. He has proficient, knowledge in various techniques, which include light scattering, laser diffraction, zeta potential, and molecular weight determination. Many of those topics have been covered in today's session, and he's the best person to deliver right on the fundamentals as well as the applications. So, with that brief introduction, I now hand over the floor to Mr. Manoj to take this session ahead. Sir, over to you.
Thank you, Edna. Thanks for your kind words. Yes. I hope the screen is visible.
Yes, sir, your screen is visible.
Okay. So welcome everybody to today's session on particle size analysis. So what we are going to cover in this session is essentially on a few analytical techniques. We'll also see what's the exact definition of size, what kind of different instruments, what kind of techniques are available. And I work with Devlata Technologies. We primarily sell particle size standards. So we'll talk about that later. And I worked primarily on the Brookhaven instrument a lot. So quite a few of the analysis results that I'm going to present would be from that instrument. But it is possible that, I mean, there are other companies also which make this instrument, similar kind of instruments, and those results can be reproduced on other kind of instruments as well. Okay, so let's begin that. Okay, so we'll start with, this is the outline of the presentation. We'll start what is particle size, what is the concept of particle size, then we'll go with particle sizing techniques, different kind of techniques which are available to us. Then primarily we're going to discuss three different techniques. One is based on sedimentation, one is on static light scattering, people know it laser diffraction or me scattering, and then we'll cover dynamic light scattering. Now, dynamic light scattering is more useful for people who are working in the nanotechnology field, and we will summarize all these techniques, what kind of size range they can cover, what kind of samples they can do, what kind of accuracies you can expect, and so forth. If you have any questions, I think you can put that in the chat box. I think the Venture Center team would take up those questions, maybe bunch few questions together. So if there are similar questions, I think we can bunch those questions together. If you feel something is very important and you want to interrupt in between, I think you're welcome to do so. So don't bother about waiting for the session to get over and then ask your questions. You can interrupt in between as well. Okay. So let's begin with what is particle size. So as you know, it's a very critical parameter. Quite a few of the properties and materials that we handle on to day-to-day life, whether it's industrial or whether it is commercial things also, particle size plays a very critical importance. Okay, so it can be used as a quality and performance indicator. In fact, that is what it is used primarily in the industry. And we'll see what kind of industries it can be. It is fairly popular. It has also impact on the material properties. For example, if you want the flow of the particles or how the particles can be compacted. When you say compacted, it could be in the sintering process for metallurgy industry, flowability of particles. So it is very important. What happens is that large and more spherical particles, they will exhibit a better flow properties as compared to irregularly shaped particles. That is what we have been observed. Okay. Smaller particles will dissolve faster. So if you are preparing a solution or a suspension, they're easy to dissolve if you have smaller particles, and they will also lead to a higher viscosity. in comparison to, let's say, larger particles. Stability, if you are studying stability, mainly, let's say, from the paint industry, people will be very interested in the stability, or from even the pharma industry. The smallest particles will lead to a higher stability. Of course, the zeta potential also is important. So both of them together would lead to stability. Other properties like, say, for example, if you're looking at paint, the color of the can be affected by the particle size. We have seen in examples where the particles have the same chemical nature, but the color looks slightly different, and we would resolve it using a particle size analysis. There are other properties as well that can be affected. So as you see, it's a various industries it is useful. I just listed a few of these industries that, I mean, even the audience would be from. So in paints and pigments, the gloss and the appearance of the paint would get affected. The reflectivity of the highway paints also plays an important using particle size. In food and beverages, color and flavor of products like cocoa powder can be affected by that. In fact, cocoa powder is just one example. There are other products also it can be useful. Hydration and strength of cement. Cement also, actually, in cement, concrete, when you prepare, the particle size is important. Metallurgy, as we said, when you have how you want to compaction or say sintering process, that time the particle size is important. In healthcare, how do you understand the pharmaceutical efficacy? So what kind of particles? It just showed a diagram where human the air path is shown basically. So which parts get affected by which particle size. And of course, cosmetics. So the appearance and the shelf life of cosmetic products also get affected by particle size. So when you say particle size, is it possible to define size by a single number? Something like, let's say I have a particular number, and if I want to compare two sizes, if I say a single number, is it possible to do so? So let's say, look at some of the particles. These are perfectly spherical particles. So yes, probably they will have a distribution, but that distribution would be quite narrow. This is a slightly a zoomed image of the same particles. Okay. So by looking at these particles, we feel that you can have a single number which can define the particle size. These are images of some of the standards that we deal in. So they're perfect spheres. In fact, these are ranging from few nanometers to few microns sometimes. So this is a particle size range for this particular standards. And they're very stable. But they are perfectly spheres because they are meant to be standards. But in practical, it's actually not so. I mean, these are spherical, but if you look at some other particles, for example, this one, you won't find them spherical at all. In fact, if you look at the next slide, I mean, they're very irregular shapes that you can find in nature. The way the clay particles behaves would be very different. It has, I mean, different dimensions altogether. Or if you look at sand or slit, the kind of sizes that you'll encounter or the shape of the particles that you encounter is going to be very much different. In fact, these are some of the sizes that we sometimes encounter in real life. And it is very difficult to say that what one number we can associate with them. In spite of that, it is always very convenient if you have to come up with a single number to define a size for them. So you cannot say that it will have one single size, but if it is convenient to have it one single number, that is preferable. So what do we do is that we have come up with a concept what is called as the equivalent spherical diameter. So this is what is defined by ISO as the diameter of a sphere having the same physical property as the particle under examination. So typically when we do the particle size measurement, we don't measure the size directly. We measure the physical property which is associated with the size. For example, if the particles pass to the same size aperture in a sieving analysis, then we say that these particle sizes are same. It is possible that some of the particles are spherical, some of the particles are irregularly shaped, but if they pass to the same sieve, then we say they are of the same size. So then we get a single number. It is very easy to compare. So on the right-hand side, you can see an image of a sieving method so as you go down the sieve size decreases, and you can get smaller and smaller size as you go down the sieve. So this is one particular method which is very popular, which is a very old technique to measure particle size. Other is if the particles are in suspension, let's say you have a homogeneous mixture of particles and you let them sediment or settle down, particles of the same size will settle at the same rate. So if you see the yellow particles, as the time progresses, the yellow particles settle down first, then the green, and then the red. So the yellow particles, you can say they are of the same size. The smaller size is green and the smallest is the red one. So this is another way of having a particles classification. Now the advantage of here is that these particles could be of different nature. They are not necessarily of the same material, but they could be different materials. So in that case, sometimes it is very difficult to know how exactly we can call of both of the same uh, size. They have a different density possibly, or the shape may be different. But so long as they're sedimenting at the same rate, we can say that they have the same particle size. Or if you consider light scattering or a static light scattering, in this case, if you measure the intensity of the scattered light at a given angle, or say multiple angles, for particles analysis, one single angle is not sufficient. You have to measure at multiple angles in case of static scattering. So if the behavior is same for two particles, we can say that the particle size is same for both of them. Or in case of, let's say, electrosensing zone, it's the volume of the particles. So if the particle displays the same volume liquid, then those two particles are of the same size. Or in case of imaging, what is the area which is projected to the surface, or what is the area which is projected by the particles onto the thing. So this is also used. Now if the particle is standing up like a needle, it will still have a same size as an equivalent other particle, which is like slightly flatter. But they may have, for us, basically, when you see as a layman, we feel that those two particles are different. But for the application based on imaging, they will be same size. So based on this, there are different kind of classification of techniques that we can come across by size range. Now, this is the most common classification where you do that. Whether this instrument measures nanoparticles, or some say it is a micron size particles, or dry powder, or a wet powder. So something's based on imaging, something is not based on imaging. Something is based on the degree of separation, that is fractionation. Or it will be after doing all this measurement also, whether it can give an intensity-based weighing, or a volume-based weighing, or a number-based weighing. So different kind of weighing techniques also are there. Now, these are mathematical artifacts which are applied after the primary analysis is done. This is not the basic analysis directly, but the analysis done using maths. And what is the information content? What kind of information other than the basic data it can give? So that may be very useful from the quality analysis purpose. So these are some of the techniques and their typical size range that exist in market. At the top, you'll have the sieves. Sieves has a very coarse kind of size, mostly about 1 micron. If you go on the lower side where you're using DLS or say TEM or SEM, you'll be able to measure nanoparticle sizes. Okay. So there's a host of techniques sometimes is there. Now, all the techniques or one technique may not be sufficient for your analysis. You'll have to choose the right technique for your kind of particles, because industry-wise, the size range that you will encounter on a particular industry would be varied. So it would be best if you decide which particular instrument is suitable for your kind of analysis. There is no single instrument which will take care of all the requirements. We'll just look at this time of transition or time of flight. Earlier, electro and optical zone counters. We have Fraunhofer diffraction and static light scattering. In fact, in light scattering, we also have the dynamic light scattering. And we also have something known as the diffusion wave spectroscopy. So these are also used for particle sizing. These are based on fractionation. So there are different kind of fractionation techniques. Okay, then we have the sedimentation techniques. Some simple gravitational base as well as using centrifugation, dynamic light scattering, and then we come to the microscopy. So in microscopy also we have basic optical microscopy, and then you have the more high resolution and for lower sizes, TEM and SEM. So in the classical techniques, we had sieving and to some extent, I would say even microscopy. So people used to have a microscope and then see the particles, and using the magnification they had, they could predict what is the size, but it was a very tedious method. I mean, you can just see a small portion of the whole particle size and then you have to compare. Okay. So measurement of the size also was not automated. Now there are automated techniques. There are basically softwares to do that for you. But still, people use these techniques tremendously. In the more modern techniques, we have sedimentation, both gravity as well as centrifugation. Then you have light scattering. In light scattering also, we have the static or the diffraction based light scattering and the diffusion wave spectroscopy, and you have the dynamic light scattering. Okay. Static diffraction light scattering, people also refer to as a more generic term, is the Mie scattering. So we'll now look at one of the main techniques that we have, first technique that you're going to study, and that is the technique based on sedimentation principle. So as we discussed earlier, in sedimentation, what we have is that we take a sample and we just let it remain in, make it steady, and the particles settle down based on the gravity. Now, there are few things which act over here. One is the gravity. One is the density of the particles relative to the suspension medium and the particle size. So as the particles start sedimenting, they essentially they achieve something known as a Stokes velocity, that is a terminal velocity, beyond which the particles would not accelerate further. So they are going to sediment at rate. As you keep more time, basically the bigger particles will settle down first, then you come to the smaller, and then the smallest one start settling down later. So you have to measure the time it takes for the particles to settle. So if you have the d is the distance, that is how the calculation goes. So we'll look into the calculations in the next slide. So if you have t is a time which is measured in seconds. So as you start basically introducing the samples and then the particles start sedimenting. So this is the formula at which you do it. Now the only unknown in this case is your d, that is the diameter of the particle. Okay. So you know the viscosity of the liquid, you know the distance it travels from the place where you have introduced the particle to the place we have kept a detector to detect the particle, and gravity is constant. And delta rho is the density difference between the two. That is the rho of the density of the particle minus the density of the fluid or the liquid, whatever you're measuring, whatever you used as a suspension. Now, what happens is, this is a typical time it takes for particles to sediment. So if you have, let's say, a 50 micron silica, it would basically sediment by 1 centimeter, it will travel around 4 seconds. Or if the polystyrene latex, it will take around 2 minutes. But as you go down the size, okay, and also on the density of the particles. So as the silica is more dense than polystyrene, so it's going to sediment faster. But polystyrene is going to take long time. So the same size as we go to 1 micron, silica would take 3 hours, but polystyrene latex would take 100 hours. So just not possible for do most of the analysis with such kind of time periods involved. So what we do is that in the previous slide, if you see, there is nothing much you can control except G. Now G, you can do, or you can modify the G by using centrifugation. So you rotate the disk, introduce the particle at the surface of the liquid. Here, your detectors are not necessarily placed in the bottom. They will be placed somewhere in the radius of the disk. And as the particles basically centrifuge and go towards the periphery of the disk, you can then do the calculation. So since the G is now different over here, it's going to be based on the RPM of the centrifugation disk. So that calculation will go over here, and the formula is given on your screens. At the same time, the distance is the distance where you are introducing the particles on the surface, and RD is the distance from the center where you actually kept the detector to detect the presence of the particles. So this is a formula which is used for calculation of the particle size. Okay. So sedimentation differentiates mass by particles, and diameter is just equal to 2r. So we solve for mass based on sedimentation time and calculate d based on the equivalent spheres sedimentation time of the same mass. That is how it is calculated. So here in this case, sometimes you have the detector which you are using is either an optical detector, or sometimes you even use an X-ray. So particles which can absorb X-ray, you can use an X-ray detector, or particles which do not absorb X-ray, people go for a light detector. So typical size range in this case would be, we can measure less than 10 nanometer, and you can go even above 100 micron. Now this kind of size range would be dependent on the differences in the density, as well as the viscosity of the liquid and the RPM of the motor. Very high RPM centrifuges also available, but they're extremely expensive. At the same time, simple gravity-based sedimentation instruments are also available. So depending on what size range you want, you can select the kind instrument that you have. Most of the centrifuge-based instruments would allow a normal gravity-based sedimentation as well. Okay. The sample volumes required are fairly small. You don't require a very huge sample, 0.2 ml sometimes. Sometimes if you're doing gravity-based, you can go up to 20 ml. You don't need very high concentration, or even if you use in high concentration also, it's fine, because you need very small kind of liquid. Okay. Times are slightly longer in this case, but if you have very low sizes, it can take huge time. For example, we've done some measurements for carbon black, where the distribution is right from 600, 700 nanometers, and it can go up to 10, 20 nanometers. For such size range, sometimes you have to do the measurement time for at least around 2 hours, sometimes 3 hours. So those are basically very different cases. And in fact, carbon black the majority of the people use sedimentation technique for measurement of particle size. Now we go to the next instrument that we are trying to study. This is a static light scattering. So in static light scattering, what we need is a detector which you can move with at different angles. Now, when you move to a different angle, it takes a longer time. And as such, basically, people want to do the analysis very fast. So instead of using just a single detector, the typical instrument setup is something like this. So you have multiple detectors, and you also have a small CCD array, or a kind of an array of light detectors. So that is placed very close to the zero angle. And for the higher angles, then you have discrete detectors. This detectors basically can give a value at some discrete angles. So the advantage of the first scheme is that you can vary the angle as per your requirement. But in the second case, you have fixed angles only. Now the scheme which is presented first is mostly commonly used for measurement of molecular weight. So people who use multi-angle light scattering setup and want to use molecular weight, then the instrument setup which is shown on the left is what is preferred because they can vary the angle. Okay. And in the case of the right, it is mostly used for particle size analysis using Mie scattering or Fraunhofer diffraction. The advantage of this technique over the other two techniques that sedimentation and the DLS is that you have a sample reservoir, and in this sample reservoir you have an option. Either you can have a dry sample or a wet sample. So wet sample is what is basically you have a suspension prepared, and that is what you let it flow through the sensing zone. But you can also have a dry sample, something like an agitator. So agitator-based dry sampling also is possible in this kind of instrument. So we have the advantage of using dry as well as wet samples in this case. Okay. So the intensity measurements are made at several scattering angles. Mie theory or the Fraunhofer diffraction is then used to extract size information. Okay. You can measure high particle sizes, hundreds of microns also can be easily measured. But at very low sizes, I mean, you might encounter failures. So you need to be sure when you're measuring very low sizes, whether the instrument is giving you the fair results or not. A typical guideline for doing measurements on this kind of instrument is that for all particles larger than say 50 microns, if you have just a Fraunhofer based calculation, it will give a good accurate particle size distribution. Okay, but if you are smaller than 50 microns, the instrument should be capable of handling Mie theory as well. Some of the instruments have both the options. Some of the instruments will only use Fraunhofer diffraction. So you have to just be a guard which particular technique which is used finally for the calculation of the particle sizes. Fraunhofer gives good result basically for certain sizes, and this particular which one will give you best result and which particular calculation for you should use for the for your particles, you should know a priori. Most cases basically Mie is good, and it can give good results if you have know the optical constants properly. The size range in this case is fairly slightly narrower if you say compared to sedimentation. It is around say 0.5 microns. Sometimes some instruments claim to even smaller than this, and it can go even higher. I mean, 1 millimeter is fine, but it can go even higher. Depends on whether you can make the particles in suspension, because higher size particles are difficult to keep them in suspension. And that is a challenge because you have that sample agitator and the flow cell. You need to keep all the particles in suspension. bigger particles, if they sediment down or settle down in the sample agitator, then they will not appear in front of the detector. That is the issue. So you need to have a good sample agitator and a flow-through cell for having the complete size range. If you're using a static static cell, not a flow-through cell, then your sample volume could be lower. But if you're using a sample agitator and a flow-through cell, you'd require a slightly higher sample volume. Concentrations are not that much of an issue in this case. You can measure at different concentration too. The measurement time is fairly small, but if you are having, huge widths or say bimodals, you might like to do the analysis for a long time for the analysis or the results to become stable. In this instruments, essentially, when you start measuring, the intensity at the various angles are shown on the screen. So once the uh, intensities remain stable, okay, you can stop the analysis, or the time you can stop, and whatever results or calculations the software is supposed to do, you can ask the software to calculate and give you the results. Next, we come to the topic of dynamic light scattering. And in dynamic light scattering, we'll see what is DLS. We'll see some examples. Okay. So dynamic light scattering is known by multiple names. It is some kind of a time-dependent light scattering. Okay. So sometimes people know it as photon correlation spectroscopy 2, or in some old literature, you'll come across quasi-elastic light scattering. So all these three techniques are essentially the same. They are same. So if somebody says photon correlation PCS or QELS or DLS, they mean the same technique. So don't get confused by the different names. Dynamic light scattering is the most common name which is used now, and that is what is now referred in literature as well. So how does it work? So particles which are in suspension, let's say, they'll go through a Brownian motion. Okay. So Brownian motion keeps submicron particles suspended, and they will exist in aqueous, even or in organic liquids. So both these liquids, you will have this kind of a Brownian motion. Okay. Examples are colloids, nanoparticles, micelles. Now, if this sample is put inside, let's say you have a cell. This is a top view of a typical instrument. So you have the cell, which is a square cuvette. And in the cuvette, you have this sample. What you have is the laser, which is, sometimes you can have the 45-degree mirror, or you can have a straight line as well. And the light is incident onto the cell. So you see on the top right side, you have a focus beam, and then the light beam is passing through the sample cell. And the particles which are are suspended. So this particles are going to scatter light, and this scattered light is going to reach your detector. Now, in this case, your detector is either a PMT or an APD. PMT is a photomultiplier tube. APD is the avalanche photodiode. And they could be at multiple angles. In this case, the instrument that we have shown on the left side, it has two different angles. One is at slit S1, that is the 90-degree angle. And we have the slit S2, so that is a low angle. So 15 degree or 12 degree. There are instruments which are also using backscatterer. So they'll have something like at 173 or 174 or 178. Okay, so different kind of instrument setups are available. Each of the angle that you use has its pros and cons. But in dynamic light scattering, you need only one single angle for measurement. You don't need multiple angles as you require in static light scattering. So the signal which appears on the detector is given on the right-hand side below graph. That is the intensity versus time. So you have some intensity, some kind of a random fluctuation over the average. So if you say intensity is in terms of photons which appear on the detector in a given time period. So that is how these photons appear on the detector. If you see this intensity very closely, dynamic light scattering is trying to find out if there is any hidden information in this random scattered light, random intensity pattern that you see. Static light scattering would be bothered about the straight flat line that you see. Okay, but then it has to measure at multiple angles. Dynamic light scattering would like to see if there is a hidden information in this random pattern, and based on that, predict what is the particle size. So we'll just look at the next slide. So if you look at the intensity pattern and you divide the pattern in terms of sampling time of, say, let's say delta t equal times, each of this red vertical line is like a photon appearing on a detector. So in the first sample time delta t, you have 2 photons appearing, then you have 1, then you have 3 photons appearing. Then the next interval you have none, then you have 5 and so forth. So this is how the intensity is there. So in a static light scattering setup, you will just sum the photons for a given time period and calculate the average. That is a static light scattering. But in case of dynamic light scattering, we try to see if this some information is there. So what we do is that we have a correlation function. So correlation function from C tau 1 equal to 1 delta t to, let's say, multiple delta t's. So that is how the correlation function is calculated. And the correlation function of a particle in suspension is an exponentially decaying function. Okay. The exponential decaying function is like this. So you have the C tau. So what the hardware does, or the hardware in the sense that the instrument does, it measures the correlation function at different tau and gives these values to the software for calculation. The software does an exponential decay fit. Based on the exponential decay, it calculates the translation diffusion coefficient, dt, and this diffusion coefficient has one value called dh, which is a particle size. So in this diffusion coefficient, the only unknown is dh, and that is the particle size. The dh is to signify that it's a hydrodynamic diameter. Okay. So in this case, we measure the hydrodynamic diameter. In case of sedimentation, we measure the Stokes diameter. So these are some of the basic equations. This is a generic form of a autocorrelation function of a monodispersed sample. Okay. And we have the line width and the scattering wave vector. Scattering wave vector is a constant. Theta is the angle at which you measure. N is the refractive index. And in the Stokes equation, dt is your diffusion coefficient. Kb is the Boltzmann's constant. T is the temperature. Eta is the viscosity of leakage. The unknown factor is dh. That is what you measure. So on this, we are showing you the result of Triton X100 micelles. On the right hand side, you have the correlation function. On the left hand side, you have the distribution. So if you see, this size is extremely small, and the effective diameter that is given over here is around 9.31 nanometer. Many of the times, people when I have come across DLS users, they don't give a good value or good understanding of the correlation function. And the correlation function, even if it is crooked, they still get some size. If it is typically crooked, it will give some other values, and the software will still do some calculation and give you some size, but that size may not be very good or accurate for your measurement. This is another size. It's lysozyme. The effective diameter is very small, 2 nanometer. Here also, if you see the correlation function, the shape is same as what we are expecting, and that's why the results can be relied upon. How small you can measure? You can measure extremely small sizes. Okay, I mean cholesterol in meek, you get around 0.6, polystyrene in THF 1 nanometer. I have myself not measured below 1 nanometer. Yeah, to 1 nanometer I have measured myself, so that's fine. But there are people in labs who have measured even smaller. But as you go smaller in this size, the sample preparation becomes extremely difficult. So one has to pay a lot of attention to how the sample is prepared. This is an example of how the bimodal distribution is there. 92 and 200 microns. Okay, nanometer, sorry. So there are some disadvantages of particle size. If you see the previous slide, you can see two different sizes that the instrument can show. But many times, DLS will not be able to resolve two sizes very easily, especially if they are slightly more closer than what they are right now. It will not be able to resolve their two particle sizes present in the sample. It will just give one single number, which might be biased towards the higher size particles. That's what typically happen. So the disadvantage of particle size using DLS is it's a low particle resolution of particle size distribution. Okay. Sample preparation is very important. So if there are large particles, they would cause error. This is mainly because of the fact that the intensity of the scattered light is directly proportional to the particle size diameter raised to the power 6. So if small particles are there and there are very few large particles, those large particles, when they come in the path of the laser beam, they're going to scatter so much of light that the all other small scattering, the light from the small particles, are going to get obliterated. So it is not suitable for very broad particle size distribution. So if you have very broad particle size distribution, you might have trouble in getting the good results with this instrument. Since it's intensely weighted, it will overshadow particles, small particles in distribution. So that is what we covered earlier to some extent. But in spite of that, DLS is very useful. It's very fast. It's precise. When you say precise and reproducible also, it is absolute. You don't need any calibration for this instrument. I mean, you don't have to calibrate this instrument. That if you don't get a result with these standards, then either, I mean, there's something wrong with the instrument, or there is something wrong with the sample preparation, or something wrong with the standard. Either of the three is there. You can't basically trick a number and say, I have set up the calibration constant for this instrument, and that should be valid for another 6 months. No, nothing like that. It has to give you the correct result all the time. Okay, it is a wide size range. Okay, it can do aqueous as well as non-aqueous sample, but DLS will not be able to do dry samples. Powder samples, dry powders, it cannot do. It has to be suspension. Since it is intensely weighted, if there is a kind of aggregation happening over time, that can be studied as well. So let's look at the operating size range of DLS, less than 100 to greater than 10 micron. Again, this is very difficult. I mean, typically 1 micron, 2 microns, you might be able to get it easily. But if you go slightly higher on the micron scale, keeping the particles suspended is going to be a challenge. You can't use an agitator or flow-through cell in this case, mainly because we need the particles to be in Brownian motion. So you can't use any kind of external agitation in this case, because then you won't get a true Brownian motion the way you desire. Sample volumes can be extremely small. I mean, you require a very small volumes. I think 10 microliters or even typical volume is around 3 ml. You can work with low it typically works with low concentration. But if you use backscattering, you can go for higher concentration as well. But using backscattering, you have to just worry that the chances of multiple scattering within the sample should be reduced. So measurement time is fairly fast. As you say, seconds, if you want to do 3 minutes is what is very typical. But if you have bimodals, then you like to give it a more time for measurement of the size. Okay, so that's what we cover with the DLS part. And like to see which, if you can get to know a perfect particle sizer. So when you're trying to make a purchase of a particle size analyzer, everybody will look for a perfect particle sizer. So what are the typical characteristics of a particle sizer? It should measure from 0 to infinity, infinite. Okay. It has a perfect accuracy, a perfect precision, infinite resolution. When I say resolution, means if there are two sizes very close to each other, it should resolve both the sizes accurately. Okay. And it should measure in, no seconds. Absolutely. I just put it, I should get the result immediately. Okay. And it should cost nothing. So such a particle sizer does not exist. So what you have to do is that you have to really narrow down your choices. What kind of size, what kind of particles, get some samples tested at different instruments, at different makes, different techniques, and see the suitability. Also compare the results where you're going to use it for. For example, you might be selling this chemical or the powders to somebody, and they would like the analysis to be done on a specific instrument or a certain type of instrument. So like to get this information from there and then do the analysis on a similar kind of instrument. Otherwise, if you buy a sedimentation, if your customer is expecting based on DLS, then there will be a mismatch. Those two instruments may not give you the same size. It may give the same size, it may not give the same size. So you have to be very careful regarding what kind of instrument you are using, what kind of technique you're using. Okay, because I've seen some of my carbon black customers who have bought a DLS instrument and they have failed miserably, and they have to go for a sedimentation based instrument later on. Okay, in pharma industry, DLS is also there, as well as me scattering based instruments are fairly popular. So both these instruments are popular in pharma industry. So depending on the industry, you'll have to select which kind of instrument would be suitable for your kind of analysis. Okay. In the summary, I've just prepared the kind of what is the size and what is the accuracy and this. So as you see in the SLS differential diffraction or a me, we can do wet as well as dry. But for sedimentation and DLS, it has to be a wet sample. You can't do dry samples in this case. Okay. But sedimentation has the highest resolution. In fact, the resolution of sedimentation-based instruments is very high. If you have two particle sizes very close to each other, sedimentation can find those two sizes very easily. The precision of all the instruments is relatively very high. Okay, and the accuracy also is good. Sedimentation is exceptionally well in terms of accuracy, but they are good. But resolution-wise, sedimentation will score over SLS as well as DLS. So make a good choice. What kind of instrument you want to buy? Get some analysis done on samples or tested at different laboratories or even your vendors, and then get it compared. And then only make a decision to which instrument that you want to purchase. I just listed the sources from which I have picked up some of the data. Okay. And now I think we are open to questions.
Yes, thank you, sir, for taking us through that detailed presentation on the techniques and applications of PSA. I think you covered most of the widely used techniques. There are a couple of questions in the chat box that we have received. So I'll quickly run you through that. So the first question, just a minute. Yeah, the first question is from Amit, and he says that there is another technique known as microscopic technique, which they claim to be ideal to measure particle size. Could you please enlighten on the method of using microscope for measuring particle size?
As I said in the one of the slides, microscope is used for measuring particle size. Now, as you go lower on the size range, typically you need a higher and a higher magnification. So there is a limit on the magnification that you can do in microscope, because there are some optical aberrations which come in making of those lenses. So its size is getting limited by that. Second, the magnification that you have for microscope is not exact. So even if it is written 10x, 50x or 100x, that x is not perfect. That 10 may be 10.01 or something like that. So you need to have a good calibration standard for the when you're using a microscope. In microscope, it will only see a small portion of the whole sample, because you can't cover the whole sample. So there are now microscopes which have a motorized slide. So this will move the sample from small window in a small portion of time, and then it will cover the whole window. Those kind of microscopes are also available, but then the cost keeps on going up, and also the time required for the analysis. So microscope techniques are there, but good for something like, I would say, slightly below 1 micron, yes. Above, no problem. But as you go lower on size, zero point 0.1 micron and below, you'll have difficulty with using a microscope. But if you considering TEM or SEM, yes, definitely they'll go much lower in the size, but they're also much more expensive too.
Sure. So I hope, Amit, your query has been clarified. Moving to the next question, it's from Rohini, and she says, like, how to choose the angle in DLS analysis.
Can you just repeat?
How to choose the angle in DLS analysis.
Okay. See, the angles have certain biases along with them. So if you look at the lower angle would be biased towards the higher size particles, whereas the higher angle, that is a backscatter, is biased towards the smaller size particles. So if you have 90 degrees, typically it has balance, but at 90 degrees you'll have the least amount of scattering. So if your particles are scattering very small amount of light, then probably you might like to go for lower angles or higher angles. And based on you want to have the bias removed. If you're looking at small particles in suspension, then backscatter is what we would prefer. But if you say that the particles are scattering reasonable amount of light, then I would stick with 90 degrees. But in 90 degrees, you have to make sure that the particles is fairly dilute. If the concentration is high, there may be too much of internal scattering, and that may lead to wrong results.
Yeah. Rohini, I hope that the query is clear. If you have any related questions to that, you may unmute and ask, because I do see that you have further questions over there. So Rohini, if you're still with us, probably you can unmute
Yes,
and elaborate on your query. Yeah,
yes,
please go
ma'am.
ahead.
Thank you. Uh, Good afternoon, sir.
Yeah.
Sir, I have a protein sample. Means my subject is fluorescent protein nanoparticle. I have prepared fluorescent protein nanoparticle, and I done means lot of time DLS analysis of that on same means instrument that Brookhaven, that which is so, sir, there is a three different angle in DLS, that is 15 degree, 90 degree, and 173 degree. Sir, if I don't know that what side should come, then uh, I choose the 90-degree angle for that. Yes.
See, as a default, you can go with 90 degrees. As I said,
Okay.
it will
Hmm.
not have bias towards higher size or lower size. But as you gain more understanding of your samples and
Mm.
your sample preparation techniques also improve, that
Yeah.
is, you don't have any unwanted particles in your sample,
Mm-hmm.
then you would like to compare the result with the other angles too.
Okay.
Okay, if your sample is clean, I mean, there are no higher size particles, then probably the other angles also will give reasonably good results too. But if you're not sure, then typically you start with 90 degrees.
Means, sir, each time I have got different result. Means there is no reproducibility in my sample during DLS
At
analysis.
one single angle or different angles?
Yes, sir. At one single angle means I have tried many time with 90 degree.
Okay.
Oh,
We need to work on your sample preparation. If you can share some data through Edna, I can help you identify exactly the issue with your sample.
okay. Thank
Sure.
you.
Rohini, you can write to me, and then probably we can take this discussion offline. At this point, I would also like to mention that we conduct monthly consultation clinics where anybody who has any query on any particular technique, they can reach out. They can enroll for that. It's a free of cost, program that we run, and as part of that, you'll get 30 minutes free of discussion with one of our experts on that particular technique, so you can stay tuned for that as well. But for this query, you can write to me and we'll be happy to assist you ahead.
Yes, sir. Thank you.
Yeah. Yeah. Thanks, Rohini. Sir, we do have a few, questions in the chat box. So if you can spare another 5-10 minutes, would that be okay?
Yeah, fine. Go ahead.
Yeah. The next query is from Dipti, and she is asking how to know which solvent for, dispersing the samples. So basically, I think she wants to know how to choose a right solvent to disperse the samples for DLS measurements.
Okay, for DLS measurement, your sample should not, first of all, be interacting with the liquid at all. So whatever solvent you are choosing, if it's going to react with your sample, I mean, that's absolutely no. Second is, let's say we have 2, 3 choices. Okay, water is that way a polar thing, so it's going to attract a lot of dust. So if you can do the suspension in things in other than water, it is preferred because then they're easier to clean the higher size particles if it is a non-polar solvent. With polar solvents, obviously removing dust is going to be a major challenge, and it's going to remain that way. So those two factors you should consider. Third is that what is the kind of sample cells that you're using? If you're using acrylic cells, then probably it will rule out acetone. Then you have to go for glass cell. Those are more expensive. So it's an expense. It's also the kind of reactivity, chemical compatibility with the things. And otherwise, there is not much of a problem. Most of the instruments will have a chart of the liquid, and it will also have the chart of the viscosity of the solvent and the refractive index, because those two parameters go into the calculation of the DLS particle size, and they will have, the instrument will have a table internally it will have a table of the viscosity and the refractive index of the liquid at different temperatures, because you have a very good temperature controlled oven where you keep the sample cell. So you can take the sample from different temperatures. You can measure just about dew point right up to 100 degrees centigrade. So whatever sample solvent that you feel comfortable you can use. Make sure that it is chemically compatible with the sample and the cell that you're using.
Sure. So, thank you, sir. And I think the follow-up question, by another participant was on how to prepare solutions for DLS. I think you've already covered that. She wants to know what should be the dilutions for DLS particle sizing. So, any insights you'd like to share about dilutions that we prepare?
See, the theory says that there's only one particle in suspension. Okay, I mean there should not be any particle to particle interaction. That is the how theory goes about. Now, another particle in the suspension is going to, I mean, there is going to be some interaction. So a reasonable method to know that there is no particle interaction between two particles if they're in the same suspension is that if the distance between two particles is greater than, let's say, 20 times the diameter. Now, this is a thumb rule. There's nothing like exact in this. So we assume that if the distance between two particles is greater than 20 times their diameter, then they are not going to interact with each other. So that leaves you some scope. Now, based on the volume of the particles that you are having and the suspension volume, you can have a fairly good estimate of the number of particles you can have in the suspension. Okay. Now, this is all like calculation and those work. When we are doing the actual measurement, what happens is that, let's say we start with one particle in the suspension and then you measure something. It's going to be hell of a time getting a stable correlation. You're not going to get it because the particle may not come in the path of the in the incident light. So you need to have a reasonable high concentration. So as you keep on increasing the concentration of particles, your correlation function would start appearing. And then you'll see that it's becoming stable or shorter and shorter period of time as you start increasing the concentration. And then you also be able to calculate the particle size based on that. Now, let's say we have one single particle size, so the diameter you are getting. As the correlation functions become stable, it's going to take shorter and shorter time for it to do the same analysis as you keep on increasing the concentration. So any further increase in the concentration is going to shorten your analysis time, leading to the same particle size. But at some point, it's going to happen is that you increase the concentration beyond that, you are getting a correlation function, but the size is decreasing. Now, that is a concentration where you have a problem because at that point, there's the chances of multiple scattering happening within the sample. And that is why the size is now started reducing. So you have to stop. You have to do the analysis at the concentration before that. The highest possible concentration where you are getting a stable size right from lower to the highest. So that is the optimum concentration at which you are getting a stable size without any multiple scattering. So that is the optimum concentration. Now you have to do with some experimentation. You start with one particular concentration, you get some result. You get a higher concentration, you get some result. Then you do some intermediate, and then you can arrive at the optimum concentration for your sample. Now, if you do for a different class of samples, probably you have to do the same methodology again, arrive at the right concentration, and then go for it.
Sure. So I think it involves a lot of, before the real experiment, it will involve a couple of experiments to even come to the right concentration.
Yeah.
Sure. I think this is the last query that we will take up before we close the session. So this question again is from Dipti, and she says that for DLS, you said it is not suitable for broad PDS. Will you share the range? So, Dipti, if you're Dipti Bidwai, if you're on the call, do you want to unmute and just clarify on this? I'm not very clear what answer you're seeking.
Yeah,
Dipti?
yeah. Am I audible?
Yeah. Yes, you're audible.
Yeah, yeah. I just wanted to ask that sir have shared in disadvantages of DLS that there is not possible to have a broad range of particle size distribution. So he haven't mentioned any kind of a range. So will we be able to get any kind of range for that?
Okay, let me answer. See, when I'm saying it is not good for particle size, broad particle size distribution, we are always comparing with some other analysis.
Yeah, yeah.
So this is in comparison to, let's say, you are having a sedimentation technique. So
Mm.
sedimentation technique is good for very good wide particle size distribution.
Okay.
Okay. But if you were to do the same analysis, let's say the same sample in DLS,
Mm.
okay, your results would be completely different.
Mm.
And you feel that the size distribution that I got in the sedimentation, why I'm not getting the same size distribution in DLS?
Mm.
Because of the biases of the DLS, you may not get the broad size distribution that you're getting in sedimentation. It's
Okay, it's in
always in
comparison.
comparison to some other thing. It is never in, say, an absolute measurement for a particular measurement. So it is nothing like it will for, say, 100 nanometer size distribution is good or 200 nanometer size good. and beyond that it is not good. Nothing like that. It just in comparison to some other techniques.
So, sir, to extension of this question, I just want to ask a small question.
Yeah, go
Uh,
ahead.
yeah. So, if it's outside the range, let's say if, some instrument is having 1 nanometer to 10 microns size range. So,
Mhm.
if our samples falls either more than 10 micrometer, or it won't be possible at 1 nanometer, but if it is lesser range is also out of the range. So, will it be giving any what we can say garbage value, or it won't give the repeatable value for our analysis? What will be
Um,
the analysis result for that case?
if you have a very broad size range, let's say some sample you're having a size range, the size is beyond 10 nanometer to even lower than 1 nanometer. If one single sample, it's very difficult to have such a sample.
Huh, huh,
Okay. So in that case, what is going to happen is that in DLS, if you're measuring,
huh.
smaller size is never going to get registered.
Okay.
Okay, you are going to see a bigger size only. Even though by numbers, the smaller size are large in number.
Huh.
Okay, this bigger size particles are going to scatter so much of more light
Okay.
that the smaller size will never get registered.
That's what, okay, because with us it happened. So our particle range was around 100 nanometer, but we were trying to find it out in some bigger size range. So it was not showing. It repeatedly showing different sizes at different times of analysis. So that's why yes.
Yeah. So you really, as far as the choice of the technique that you're using and the sample preparation that you're doing, and what is your interest? See, many times you see these evidence of nanoparticles, let's say using TEM or SEM.
Hmm, hmm,
Okay, you see that, yeah, my sample has smaller size. So when you
hmm,
do this analysis, they will narrow down to the area where you have nanoparticles and it will show that yes, nanoparticles are present.
hmm, hmm.
But DLS is an ensemble technique. Ensemble in the sense it's not deterministic that only this particle will measure and it will not measure this particle. Any particle which comes in the path of the light or the incident light is going to scatter and that's going to get come to your detector.
Even if its number is less also.
Absolutely.
Okay. So its precision is more in that case.
Yeah. So what happens is that let's say you have a 100 nanometer particle, okay, and
Huh.
you have 200 nanometer particle. Let's
Hmm.
say same number,
Hmm.
okay. The
Okay.
200 nanometer particle is going to scatter something like 64 times more light than the 100
Okay.
nanometer
Okay. Understood.
because it's the
Understood.
particle size raised to the diameter raised to the power 6.
Okay. Okay, sir.
So then it becomes a problem. So if you now let's compare from 100 nanometer and a 10 micron particle. The 10 micron particle scatters so much of our light, your 100 nanometer particle will not get registered at all.
Okay.
So you
Okay,
need
sir.
to eliminate the unwanted particles somehow by using filtration, some other technique, so that those particles don't come in the path. So the solvents that you use, the place where you measure the or prepare the samples, the chambers, the vessels that you use, they need to
Mm-hmm.
be worked on a bit.
Okay. Okay, sir. Thank you. Thank you so much, sir.
Welcome.
Yeah.
Hello, sir.
So,
Excuse me.
yeah.
Uh, I want to ask one question.
Rohini, just in the interest of time, would it be okay if you share your queries over email so that, we can then take it up separately?
Okay. Okay.
Yeah, yeah. Thank you. Thank you for your understanding. With that, we come to the end of the session, and I would take this opportunity to thank Manoj sir on behalf of the Venture Center Analytical Services team. Thank you, sir, for generously sharing all your insights and inputs with all our participants. I'm sure all of them have benefited, and thank you for so patiently, answering all the queries. A big thank you from all of us. To the participants, this session has been recorded and we will be uploading it on our YouTube channel. So please subscribe and follow it. And I've also shared the feedback link. Please do give us your valuable feedback because, for the upcoming future talks, we will be considering all the feedback, both positive and negative that we get so that we can always have a, continuous improvement. So thank you all of you and see you in the next session, which will be in the next month. Thank you.
Edna, thanks a lot for giving me this opportunity. Thanks a lot. Okay.
Yeah, thank you, sir. Yeah, thank you very much. Yeah. So I'll just stop recording.